Welcome back to lecture 22.2, where we're going to talk about the relation between C.P. and C.V. Okay, just as a reminder, we are finished with chapter 6 now. We did basically 6.9 last time was our squeezer. And we're moving on to the first sections of chapter 7 in Fin on the difference in heat capacities and these general thermodynamic relations, okay? Although the 7.3, the energy equation we saw actually last time. Okay, so what do I want to do? Well, remember that for an ideal gas, we had a relationship between Cp and Cv. And that was only for an ideal gas, right? So for an ideal gas, we had Cp equals Cv plus Nr, or little Cp equals little Cv plus R. So molar heat capacities. Now, turns out we didn't have the machinery to find the general relationship until now we know our Maxwell relations. So now that we know our Maxwell relations, we can actually find a general relationship for materials. Okay, so to start with, let's remind ourselves what Cp was. Remember, Cp and Cv are like dq over t. But we now know that dq is an inexact differential. And to write this properly, then we put it in terms of an exact differential. We say it's TdS, right? So this is partial S, partial t at constant p. And Cv is partial S, partial t at constant v. Okay, so for Cp, that means that our S is a function of t and p. And for Cv, our S, our entropy, is a function of t and v. Okay? So to start to imagine the relationship between these, let's write our S in terms, because basically we just want to write our S in terms of its exact differential. So we're going to write ds is partial S, partial t at constant p, dt plus partial S, partial p at constant t, dp. And ds is partial S, partial t, constant v, dt, plus partial S, partial v, constant t, dv. Okay, so let's call this one equation 1 and this one equation 2. And we're going to find a way to combine those to get out to understand the relationship between Cp and Cv. Now, I kind of want to structure this solution like Cp equals Cv plus a term, right? That's what we're going to have, basically our general form. So what we're going to want to do is actually get rid of this dv. We're going to want to write basically Cv in the variables that Cp has, okay? So the volume is also a state function, right? So, or an exact differential. So we can write partial v, partial t at constant p, dt, plus partial v, partial p at constant t, dp. Okay, so let's call that number 3. And so what we want to do now is just combine 3 and 2. Okay? So combine 3 with 2. So you get ds is partial s, partial t, constant v dt, right? Plus partial s, partial v at constant t times partial v, partial t at constant p dt plus partial v, partial p, constant t dp. Okay, so that's nice. And so now we want to compare this equation. Actually, let's rewrite it. Let's rewrite it one more time. ds is, I'm going to actually take all the terms that have to do with dt and I'm going to put them next to each other. So this is going to be partial s, partial t at constant v, plus partial s, partial v, constant t, partial v, partial t, constant p, dt, plus partial v, partial, plus partial s, partial v at constant t, partial v, partial p at constant t, dp. All right, that's excellent. That's what we want. So now compare. I can't write that direction, sorry. Compare with number 1. Okay, so what we want to do is look at this equation and look at this equation, because we now have a chunk that has proportional to dt and a chunk that's proportional to dp. All right, so let's look at the dp part first. Well, we can see quite clearly that by, and actually a little note, Appendix B in Fin has some nice mathematical relations for partial derivatives. And this one is called the chain rule. So the chain rule, let's actually write it down exactly the way they say. So the chain rule is partial x, partial z at constant phi equals partial x, partial y at constant phi, partial y, partial z at constant phi. Okay? So that's the chain rule from Appendix B. And you can see basically you've just got partial y to partial y. That's just 1. As long as these both are with respect to phi. Okay? So then you'd have partial x, partial z, and that's exactly what you see. And so you can see by the chain rule that our partial s, partial p at constant t is the same thing as partial s, partial v at constant t, partial v, partial t, partial p at constant t. Right? So since the t's are both identical, the v's cancel, partial v's cancel, and we get this. And so we can see this term and this term, let's highlight them. This term and this term are identical. Okay, so now let's compare the other term. Let's compare this term with this term. Okay, so we get partial s, partial t, constant p equals partial s, partial t, constant V plus partial S partial V at constant T times partial V partial T at constant P. Okay, so that's just comparing those two. All right, so what does this look like? Well, you can see partial S partial T at constant P is really just CP over T. Okay, so that's just CP over T. Partial S partial T at constant V is just CV over T. And now we have to deal with this term. Okay. So this is already pretty awesome because we've got our relationship between CP and CV, but now we want to inspect this term. So what is that term all about? Well, again, this term that has to do with the entropy changing with respect to V is hard to grasp, right? So let's use a Maxwell relation. Maxwell relation, I guess is what that's supposed to say. Maxwell relation, let's do that. To convert this one. All right, so let's draw our triangle again. Our square. Triangle. Sorry about that. Our thermodynamic square. This is T and P. So we're going to do SVT. One, two, three is PTV. Okay. So now we have CP over T equals CV over T plus partial P partial T at constant V, partial V partial T at constant P. So now what we want to do is look at how these terms relate to physical measurables. Okay. So our two that we generally think about are our bulk modulus, or that is our compressibility, and our coefficient of thermal expansion. So let's make sure we know what those are. Let's write them down. So remember, our bulk modulus was defined as minus V partial P partial V at constant T, or which is 1 over kappa. Right? So our compressibility kappa was how the volume changed with pressure. So partial P partial V at constant T was minus 1 over V kappa. Okay, so that's not quite what that term is. But first let me write down the beta, our coefficient of thermal expansion. Remember, beta is 1 over V partial V partial T at constant P. Or partial V partial T constant P is beta times V. Okay, so that's great. That's going to be exactly that term, right? So this one is going to be exactly that term. But this one isn't exactly this term. So how do we deal with that? So we go back again to Appendix B, and we're going to find what's called the cyclical relation. The cyclical relation, or cyclical rule. just like our chain rule, let's write it in the book's notation first. Partial x, partial y, at constant phi. And then this one will be partial z, partial x at constant phi, and partial y, partial z at constant phi equals -1. Kind of think about this as, you know, these are all with respect to phi, right? Sorry, not with phi. That's the big difference between the chain rule and the cyclical rule, is that this one's z, this one's y, and this one's x. What's kind of nice is you can kind of see that it's a -1 because it kind of goes backwards. The x's are here, then the next ones are z, and then y's, or z, y, x, right? So if you were to imagine it x, y, z, it's kind of going backwards in the loop in the cycle, and so it's negative. So we can use that to actually come up with our relation between P and V. All right, so let's write that out. So the first one we're going to do, x is P, y is T, and z is V. So we're going to write it like this. Okay, so partial P, partial T at constant V is partial V, partial P at constant T is partial T, partial V, constant P is -1. Okay? So, this term is equal to partial P, partial T at constant V is equal to minus partial P, partial V at constant T, and partial V, partial T at constant P. And that's excellent because those are the ones we actually have, right? Yeah, it's okay to erase everything here. Okay, so we're writing this. This one now is, so let's look at what that one is. So partial P, partial V, constant T is minus V kappa. And partial V, partial T, constant P is beta V. Okay, so finally we can write CP over T equals CV over T plus, so we're going to have minus a minus kappa V, so that's just 1 over V kappa. That's beta V. And this one is beta V. Okay? Beta V. Or CP equals CV plus T. So this is beta squared, V squared, so the T beta squared, V over kappa. And this is completely general, right? We only used Maxwell relations and some of our rules of partial derivatives, our chain rule and our cyclical rule, to come up with a relation that doesn't depend on whether or not it's an ideal gas. But let's check for an ideal gas. So if you remember an ideal gas, beta was proportional to 1 over T, and kappa was 1 over P. And so we should put those in. Let's see what we come up with. Cp equals Cv plus T times 1 over T squared times V times P, which is Cp is Cv plus Vp over T. But Vp over T is, remember, PV equals nRT. So Vp, or PV, divided by T is equal to nR. So that's exactly our relationship that we got for an ideal gas. So that's good. Okay, a couple of more notes about this relationship between Cp and Cv. The first one is the sign, okay? So T is always positive. Kappa is always positive. V is always positive. Can't have a negative volume. And beta can be positive or negative. But of course, beta squared is always positive. So that tells us that TV beta squared over kappa is always positive. What that means is that Cp is always greater than Cv. Just as it was for our ideal gas. Finally, I want to point out that this second term is proportional to T. We talked extensively, so the second term is proportional to T. So we talked extensively about how the entropy, right, is the integral of dq over T, which was like Cp dt over T. And that Cp had to go to 0, so delta S could go to 0, right? And this is to satisfy the third law. And so this second term actually has to go to 0 also, right? Because Cp has to go to 0. And in fact, for most materials, Cp and Cv will all go to 0. So a typical material might look like this for Cv and this for Cp. So everything goes to 0 as T goes to 0. And that satisfies the third law. Okay, so with that, let's wrap up. We've covered our thermodynamic relations quite extensively now, and some of the things we can do with Maxwell relations. We're going to move on to kind of the last section of the class, which is talking about phase transitions. So next time, phase transitions. See you then.